So what we saw in section 3.1 is derivatives. This is one of the sort of the big calculus ideas, and this will be throughout your calculus career a very key thing. But mostly derivatives, what they are, they're the rate of change of a function at a point. So the rate of change of a function at a point. Another way of thinking about this, it's the slope of a function, but at one point. And what this turns out to be, it's going to be the way you come up with this, where you find this, is you find this rate of change, you find the slope as the same slope as the tangent line contacting this function at this point. So what this is saying is the slope of f of x at x0 is the slope of that tangent line. So the way we calculated this is we use what's called the difference quotient. And we said that f prime at x0 is equal to the limit as h goes to 0 of f of x0 plus h minus f of x0 over h. And that's the formula for our derivative. Now, later today, we're going to break away from this limit. We're going to get into something more complicated. And what's going to be happening, not more complicated, I'm sorry, something more simpler. And we'll be able to calculate these a lot faster. So what we're going to look at today, so this is sort of a little bit of a review of what we've done before. So next we're going to look at the derivative as a function. Let me grab my book here. We're going to get to some examples from the text, and not too long. So when we look at the derivative as a function, that means we're going to replace x sub 0, which is a specific point, with a generic x, and we can choose values for that x. So what we'll get is f prime of x will be the limit as h goes to 0, f of x plus h minus f of x or h. And all this lets us do is if we find the derivative at a certain location, plug x0 in for x, or plug 5 in for x, plug 7 in for x, and so on. And there you go. You can calculate derivatives along any part of the x-axis for this curve. So now there's another formula for this. And we're going to see this in action later. It's going to help us with the proof. So we'll let z equal x plus h. So if we do that, and then this means if we solve for h, z minus x is going to be equal to h. So what this means, f prime of x is the limit as h goes to 0 of f of z minus f of x over z minus x. So we're going to be working with these two formulas today, mostly with this one though. So, and we're going to get a little definition here. And we're going to exercise this definition. It's differentiation. And this is what we call the process of calculating a derivative. So let's do this. Let's say we have, and I'm just going to follow example 1 in the textbook, f of x equals x over x minus 1. So if we put all this together with our formula, f prime of x will be the limit as h goes to 0 of f of x plus h minus f of x over h. Now for this one, we're going to use the standard formula. And we'll use the other one in a little bit. But we're going to replace everything with x plus h here. A little more room. So there's x plus h, or f of x plus h, minus just f of x, and divided by h. So what we can do, we can multiply. We want to. This is what we call a complex. Well, if it's numbers, it's a complex fraction. You can call this a complex rational function. We want to make this a little less complex. So let's try to cancel these denominators. And to do that, we'll multiply top and bottom. Double. Okay, good. By the product of these two denominators. And this is a good example to go through because this, again, is kind of just tricky algebra. It's good to practice. So we're going to multiply this numerator by this thing. And then again, what we do to the top, we have to do to the bottom. We're multiplying or dividing with fractions. We got to multiply the denominator by this as well. So what that's going to do, what that'll give us, and if this is hard to see because if it's getting cut off, let me know. So multiply top and bottom. So this whole thing here is going to be distributed to these two parts here, these two rational functions on the inside. And so what that's going to give us there we go, finally. So what this is going to do is going to let us cancel those denominators. And the result will cancel this and this, cancel this and this. And so that's going to leave us with All right. So what we're going to do next is we're going to distribute or FOIL. Like these two here, we could just FOIL. And then this one we can distribute. And let me check my algebra and make sure this is looking good. Okay. -x squared. All right. So let's take a look at things that can, well, look for things that can cancel. Well, there's an x squared, negative x squared. Then we have a negative x, a positive x, and a positive hx and a negative hx. So at the end of the day, we just have a negative h on top. And so what we can do here, we're going to cancel these h's. That's going to give us -1 over x plus h minus 1, x minus 1. Now at this point, if we say allow h to be, for all intents and purposes, 0, we're not going to have to worry about a division by 0. So we're going to say this is equal to -1 x plus 0 minus 1 times x minus 1. And this will be -1 over x minus 1 squared. And that's going to be our answer. So a lot of steps in this, and I put in all the steps here. And the thing with mathematics, a lot of it's just good accounting. You just want to take your time, get all the steps in there, don't skip something. And that helps a lot. That's going to make things a lot easier. It could be a bit tedious, but if you come up with sort of your own system of accounting all the steps, that's a good way to go. So that's one way. That's one thing we can look at. Let's take a look at that alternative formula. So why would you even come up with this? So this is going to be example 2. And our f of x is the square root of x. And let's see, so x greater than 0. So in this case, we're going to do this. Oh, and I forgot to mention something in this formula. I think I left something out. I apologize. For this formula, it's not h goes to 0. So if you're in your notes, if you go back to this formula, you're going to need to make that change. It's going to be a z goes to x. So take a second. Take a second in your notes. And if you go back to this formula where it's boxed, replace h goes to 0 with z approaches x. And let me give a little explanation as to why we do that. Here, I'll wait a little bit just to give you some time to make that change in your notes. And again, this boxed formula, you're going to change h goes to 0 to z goes to x. Now, why do we write it like this? Well, if we take h goes to 0, keep in mind h was z minus x. So if h is going to 0, that's going to mean z minus x has to go to 0. And what this is only going to be possible, it'll only work if z and x become basically the same number. Or in other words, z goes to. Okay. Oh gosh, thank you. I didn't know I was muted. Ooh. Oh, just now? Oh, that's weird. Okay. Okay, well, it's back. Well, I was about to say, it's like, oh, no. Okay, good. Whew. That would be kind of like, oh, no. So what we're going to do, we're going to do this. Now, you could do another neat algebra trick here. Is you can think of this as a difference of squares. And this is sort of one of those, again, as you're going through your first semester of calculus, it's one of these kind of tricks to kind of like, oh yeah, that'll work. And it'll come back in the future. This is a neat one. But z, you can treat it as square root of z squared minus the square root of x squared. So this sets us up for that difference of squares. And so we can cancel like so. And because if you recall, let me just bring this back in. Maybe it's been a while. A squared minus b squared is a minus b times a plus b. One of these facts of factoring that they do in algebra. So that's how we can take this. This is a squared b squared, and a squared b squared. We can unpack it like this. We do the same thing here. And so what this will give us is the limit of z goes to x of 1 over square root of z plus square root of x. And so this will give us two square root of x. And that's going to be your answer. Questions about that? So again, these examples, they got some tricky algebra in there, but it's not a bad thing again to kind of practice with and wrestle with. Okay. So the next thing I want to mention, it's just notation. And you're going to see this, well, not so, a little, this is a big one for derivatives. You're going to get a bunch of different ways to represent derivatives. So let's start out with f of x, or y equals f of x, some function of x. You'll see derivatives represented this way. F prime of x, and this is a prime, is what they call it. It's not a minus or anything like that. You'll also see this written as y prime. You'll also see df dx. You'll also see d dx of f of x. You'll also see d, well, they don't do it cursive, I'll use print, f of x. And you can see this. This is a partial derivative. Though, since we only have a variable x in there, I guess it really isn't, but it's sort of in the partial derivative notation. Another one you'll sometimes see, this is kind of an old school way of doing it. You'll see a dot. Sometimes if you have a dot over f, that can mean a derivative. So this is going to, now we're going to run into this df dx business because we've seen this and okay, maybe that kind of makes sense. This is going to come up more later. We're going to talk about that more later. Why are we doing this? And this is kind of, there's some interesting ideas here. So that's just some of the notation that's there. Now, if you specify at a specific point, you can also see this. So f prime of a, or dy dx at x equals a, you'll see this. Or d dx f of x, x equals a. So you'll get these other forms of the derivative ways of representing it. If this were taking it at a specific point, a, x0 equals a, that sort of thing. So just to kind of get through that, just to kind of show you that's there. A couple other topics they do, there's a few things they mention here in this section. Still some more sort of details. So you can graph a derivative. And so what this tells you, I'm going to call in here, it's a plot of x, f prime of x, connected into a curve. Now, it might not be a curve, it might be a line. Now, what is this going to do? Well, what this is a plot of f prime of x, or the rate of change of f of x. So, for example, let's say f of x is equal to x squared. So, you graph f prime of x. And we could hammer this out, but let's say we go through all the algebra. I'll set it up, but let's say we have x plus h squared minus x squared over h. If we simplify this down, what we're going to get is 2x. So on this axis, we're actually graphing the derivative. So we have 1, 2, 3, 1, 2, 3. So what does this tell us? Well, I mean, it tells us things about f prime of x. It tells us where f prime of x is negative, where it's 0, and where it's positive. So what's the consequence of this? What's the benefit? Well, first off, it shows where, again, f prime of x is negative, 0, positive. So use those abbreviations for negative, 0, positive. Now, what this means, and we'll talk a little bit more about this later, but when f prime is negative, remember, f prime represents the slope of our function. So this means at points where f prime is negative, our actual function, f of x, has negative slopes. So if you think about y equals x squared, and here, I'll put the graph on here. sure enough, if you look at everywhere where f prime is negative, the tangent lines for f of x, they all have a negative slope. Now, if we look at where f prime is 0, well, this means f of x has a slope of 0. So here's going to be that tangent line with a negative slope. Here's a tangent line right at x is 0, or f of x prime is 0. And on f of x, that's where we get that horizontal line with a slope of 0. And then likewise, where f prime of x is positive, this means f of x has a positive slope. It's a little hard to see when it's a tangent line with a positive slope. So that's one of the advantages of studying the graph of f prime of x. It's going to tell us when f prime of x is negative, then we know our function f of x, and I could probably fill this function in. F prime of x, when it's negative, that means f of x has tangent lines with negative slopes. When f prime of x is 0, then on f of x, there's going to be a tangent line that has a slope of 0. And when f prime of x is positive, then f of x has tangent lines that have a positive slope. So that's going to be the advantage of that. So a couple other things here. We can see the size of the growth rate of f of x at x. And then finally, where we're going to see the rate of change, and this is sort of what we saw actually in number 1, where the rate of change is increasing or decreasing. So that's the idea of graphing f prime of x. So questions about that? So we want to just talk about some terminology. And this is going to be differentiability on intervals. Let's check the time. Okay. So differentiability on intervals. So first off, on an open interval, and what this means, we're going to talk about when a derivative doesn't work. These actually can fail. So we're going to talk about sort of what it means to succeed, and then we're going to look at what causes these things to fall apart. So when we talk about the differentiation, if a function's differentiable on an open interval, what that means, it's differentiable. In other words, the limit exists at every point inside that interval. And again, we're going to take a look at what happens, because so far all the derivatives we tried to calculate, they've always worked out, which is great. But we're going to look at some situations where they don't. So if you're on an open interval, we say that f of x is differentiable on a b. So if this works, this is what we're going to say. Now, for the closed interval, it's a little more complicated. It's kind of like with continuity. And we're going to see there's a relationship between continuity and derivatives. But when we're talking about a closed interval, we have a little bit more criteria. So first off, we need f of x to be differentiable on the interior of this interval. In other words, everywhere, and we're not going to consider a and b just yet. So we need that to happen. Then we need the derivative to exist at the endpoints. So we're going to have differential at A. Now, A is on the left side of this, but we're going to call this a right-hand derivative. And the reason we're going to call this a right-hand derivative so we want to find the derivative at x equals a. So I'm going to emphasize that we want to find the derivative at this point. And if you think about how we constructed derivatives, we would use that technique using secant points. And so what we would do is you'd have another point to give us our secant line. And right here, this is a plus h. That's kind of hard to see. Let me know. There's a Greek pen. And so what the right-hand derivative means, when we let h go to 0, this point's going to get closer and closer to a. And so that means we're approaching a, even though it's a point on the left of the interval, we're approaching from the right. The arrow there saying which direction we're going. But we're approaching from the right. So this means the limit h approaches 0 plus. This is a plus h minus f of a divided by h. And you might wonder, well, why 0 plus? And just to emphasize, a plus h minus h is going to be greater than 0. So that means we're approaching, or in fact, let me write it a little more illustratively. Minus a. This is going to be a positive number to the right of 0. So that's why we're using 0 plus. So we've got to have this right-hand derivative to hold. So what have we done so far? Well, we've got the interior, everything except a and b. Then we've got differentiability at x equals a. And then, as you probably guessed, we need differentiability at b. So there's that secant line. Let's see. Now this is going to seem kind of strange. This is b plus h, and I know that makes no sense based on what we've been doing. But what's going to turn out to be the case, h is going to be negative. h is going to be less than 0. So what this is going to mean are left-hand limit or derivative so this is going to be the limit as h approaches 0 from the negative side. So very tiny negative numbers. F of b plus h minus f of b over h. And so what we're going to get is that here, b plus h minus b is going to be less than 0. Or it's going to be negative to left of 0. So sort of like with continuity, when we have closed intervals, we got to look at what's going on in the interior. But then we also want to look what's happening on the endpoints. So same kind of thing. So, all right, this seems like a kind of just overdoing this. Like you're throwing a lot of abstract ideas about these derivatives existing. Well, okay, so basically it boils down to this. A function is differentiable on an interval if it's differentiable at every single point in that interval. And that's it. Now for open intervals, it's just use your regular derivative formula. But for closed intervals, you gotta use 3 formulas. You would have to use the regular formula for the interior, and then you're gonna have a rise side interval for that far left point, because you're gonna approach from this side when you do your formula. And then you're gonna have a left-handed interval, or sorry, left-handed derivative as you approach, as you work with this point on the right, because you're gonna approach oddly enough from the left. So that's the setup for this. So we've talked about these things working out. Okay, great. But there's sort of an elephant in the room here. When do they not work out? Like, when does this sort of fall apart? So let me go through some examples. It's sort of like things functions can do that can make do not work. Let's check the time real quick. So there's different reasons for this. One thing that you might see is what's called a corner. You'll lose a derivative at a corner point. And the reason is, if you take one-sided derivatives, for example, a right side derivative or a left side derivative, they're not going to be equal. All right, sorry about that. I think we're having some connection problems. So the one-sided derivatives aren't equal. So that's the problem. So the other kind of point where they don't work is called a cusp. Here. Hopefully we'll keep that internet. And so what this says is that basically the slope of your tangent lines will become positive infinity, or they're going to become negative infinity, depending on how you approach this point. Another point where these derivatives fail is where you get vertical tangents. Let's see, they sometimes say this. So point, let me draw this a little better. Where you're going to get a vertical tangent line, that's also where your derivative doesn't exist. And then finally, discontinuities. I'm going to give a couple examples here. So here I'll circle this one. Here's one example. Here's the other. And all the points of concern are going to be places like this. And let's see, places like this. These are also places where your derivatives aren't going to exist. So these are the points you kind of want to watch out for. You want to watch out for corners. You're going to want to watch out for cusps. Corners, because you get different one-sided derivatives. And just like a limit exists when the two-sided limits exist and they're equal, same issue here with derivatives. You want the two one-sided derivatives to exist and they should be equal. But for a corner, that's not the case. For the cusp, you're actually getting this issue with vertical lines again, just like this. And then with the cusp, you're going to have what appears to be a slope going to positive infinity or negative infinity. And again, just outright vertical tangent lines. Again, the slope seems to be going to infinity. So when you get tangent lines that are becoming vertical, whereas a curve like this or something like a cusp, that tells you your derivative isn't going to work. And then finally, when you get discontinuities like this, like taking derivatives at points like this or something like this, this is also where you're going to have issues. So, I mean, you could probably say, gosh, you could probably try to get like a one-sided limit here or one-sided derivative here, but you're not going to get it's not going to work out too well for a two-sided. And one of the things you're going to run up to is you could get a one-sided derivative here, but as you work with the derivative on the other side, your other point for the secant lines will be way down here. And once again, you're going to get a different result than what you're going to get up here. This one, you're going to get a tangent line kind of like this. With this one, you're getting a tangent line that's kind of doing something like this. And again, they're not going to be the same. In fact, this one's going to pretty much come out to pretty much vertical. So that's going to be an issue. So those are the things that you just kind of got to watch with these. And well, that's where things fall apart. So that's going to do it for 3.2. I'm a little late for, oh, I do want to mention this real quick. One last thing for 3.2. Differentiability implies continuity. So what this says, if f of x as a derivative at x equals c, then f of x is continuous at x equals c. So basically, one way to figure out if something's continuous, you can compute the derivative. If you have the derivative, it's going to imply that you have something that's continuous. So last thing to mention in this section. But let's move on. Let's get to the derivative properties. And these are important. I think for the sake of time, I do have the proofs for these written out. I might go over some of these later, but I think for the sake of time, I just want to mention what the properties are and do some examples. So these properties, they're computed by using the limit definition of a derivative. And if you're interested in these, they do have them in the text. But I mean, I'd like to at least go over a few of these later. But the first property is going to be this. the derivative, I'm going to use this dx, ddx format. The derivative of a constant is equal to 0. So for example, d dx of 3 is equal to 0. So that's for any constant. Now this one, d dx x to the n. And this is a formula you're going to be able to use. And this actually holds for any real number n. But it's going to be n times x to the n minus 1. Now, the proof they have in the text, they only have the proof for when n is a positive integer, but this can be extended for any real number. So if you want the derivative of x to the square root of 2, yikes, would be square root 2 x to the square root 2 minus 1. And that's going to be it. Another example, more typical. Say x to the 5th, 5x to the x. Now again, you can prove this, at least hopefully these formulas aren't too bad. Just mathematical quiver, so to speak. You know, quivers, I think. So the derivative So in other words, just like with limits, how the constant passed through the limit, the constant passes through the derivative. So what that means you take this derivative, it's going to be 7 times d dx of x cubed. So that's going to be 3 times x to the 3 minus 1. Again, we're using the formula for this up here. So this will become 21 x squared. And that's it. Questions about that? So number 4. Just like with limits, the derivative of a sum or a difference is going to be the derivative. It's going to be the sum or difference of the derivatives. So now what this does, this sets it up so you can do derivatives of polynomials. So what this means is we can take this derivative and basically distribute it to each term. And letting the constants pass through. And the derivative of just a constant is 0. So this will be 6 times 3x squared plus 2 times, oh, this is 3 minus 1, 2 times x to the 2 minus 1, 18 x squared plus 2x to the 1, and of course x to the 1 is just x. Let's see, I'm missing something here. Yeah, oops, missing a curve. Sorry. There we go. I forgot about this 2 that was here to start. So we have that 2 there, and then we take the derivative of this. This 2 will hop down, so we get 2 times 2, 2 times 2, 2 minus 1. And then we simplify, and this is what we're going to get. Now, that's great for adding and subtracting. And that, I mean, that's not a bad thing. But this is where it starts to get a little tricky. Let's see here. Probably the 2 interesting formulas for derivatives is what we call the product rule and the quotient rule. So let's see, I think this is number 5. And the product rule works like this. So what you're going to get, and there's different ways of actually stating this. They state it a little bit different. Well, it comes out the same way that I had. It's a little bit different than I had learned it, but we'll stick with their format. F of x times d dx g of x plus g of x d dx f of x. So that's going to be your product rule. So questions about that? I'm going to do an example here, but let's see, let me get an interesting example. Before we get into an example of product rule, I'm going to show you one more rule. It's for exponentials. And what this basically says, and this is kind of a nice turn of events, is the derivative of e to the x is e to the x. Doesn't change. So let's do an example of these together. So what's going to happen, this will play the role of f of x, and this will play the role of g of x. And so what we're going to get is f of x d dx g of x plus g of x d dx f of x. So that's our product rule. So plugging things in, what we're going to get, x cubed times d dx e to the x plus e to the x times d dx x cubed. So this derivative of e to the x is just e to the x. And then this will be e to the x times 3x to the 3 minus 1. So x cubed e to the x plus e to the x times 3x squared or x cubed e to the x plus 3x squared e to the x. And so you could answer it like this, or you could factor out e to the x. Or you could also factor out an x squared. So questions about that? So there's one more property to mention. and it's what we call our quotient rule. And this is the most complicated of the rules. So this is where it's different than limits, where limits you just distributed the limit and calculated it. But with derivatives, you got to follow these formulas. So if we're taking the derivative of f of x over g of x, what we're going to get is g of x times the derivative of f of x minus f of x, the derivative of g of x, a little multiplication in there, divided by g of x squared. Whew. So for the most part, the derivative formulas are fairly simple, but they start getting tricky when we get the product rule and the quotient rule. And sometimes to get out of using the quotient rule, we're going to talk about this when we get to the chain rule later, you can turn this into a product rule situation. And if you're having trouble remembering this, then you can always convert this into the product rule and then use your product rule formula. So let's see, do an example with this one. So let's say we have something like this. Well, this is going to play the role of f of x, and this is the role of g of x. So again, we're going to have g of x, d dx, f of x, multiplication in here, minus f of x, oh, let me check that again, derivative g of x. So plugging things in, okay, e to the x times the derivative of, yeah, f of x is x cubed, minus x cubed times the derivative of g of x divided by g of x squared. Now, this derivative is going to be 3x squared, or 3x to the 3 minus 1, minus x cubed, and derivative of e to the x is just e to the x. And e to the x squared, you're going to multiply the 2 and the x in this case. So you get e to the 2x. So this will be 3x squared e to the x minus x cubed e to the x over e to the 2x. And again, we can simplify this. E to the 2x is e to the x plus x, or e to the x times e to the x, which again, that's e to the x squared. So we can factor out an e to the x. We could cancel an e to the x. Yeah. 3x squared minus x cubed over e to the x. And that's going to be our answer. All right, so we've got 7 minutes left. Let's see. So here's an interesting one. We'll do one more example. There are ways, again, you can find ways out. Oh, wait, hold on. One last thing. Okay, I'm going to skip this example for now. One last thing in this section. I'll make sure we get this covered. So one of the questions that might come up with derivatives, can you take derivatives of derivatives? And the answer is yes. And we're going to find out, this is actually really important. We're going to get into something where we try to identify what are called inflection points. And we're going to use what's called a second order derivative. So some terminology. F prime of x. This is a first order derivative. If we take another derivative, d dx of f prime of x, this is going to be f double prime. Or a second order. Then we might take the derivative of the second order. So you have an f triple prime or third order. And this goes on forever. So what typically happens with derivatives, and I'll give you kind of an example of an application. Let's say we have a function, let's see, distance in terms of time is equal to, and let me go back here, pick up this formula again, 16 t squared. So here, this is going to be distance and then t is time. So this is that formula where if you take something near the surface of the Earth and you drop it, it tells you how far it's dropped. What's the distance from my hand at a given time? So it kind of does that, accelerates down. So the distance is going to be like our f of x. The velocity, v of t, is equal to the first derivative, d prime of t, or d dt of d of t, which is going to be d dt, and we're using dt instead of dx because we changed our independent variable, of 16t squared. So this is going to become 16 times d dt of t squared, which equals 16 times 2t to 2 minus 1, 32 t to the 1, 32 t. So if we take the first derivative, that's going to tell us the velocity of this pin at a given time t. So if we use 16t squared, that's going to tell you how far it's fallen. But if you use this formula 32t, that will give you the speed of this pin, how quickly it's falling, at that same time t. And now we're going to get something else. Acceleration. This is the change of the velocity. Remember, that was d prime of t. Or this will be d double prime of t. So let's go back to this. d dt of 32t, that's going to be 32 d dt of t. And this one, I'm a little cautious with this one, I'll be honest. I want to get back to you on the proof for this one, just because there seems like there's room for things to go, as they say, sideways. But what you would get is 32 times 1 times t to the 1 minus 1, or 32 times t to the 0, or 32 times 1, because anything that's not 0, anything that's not 0 is going to be equal to 1. I'm just going to make this caveat. T not equal to 0. And I'm going to go back and look for this to make sure that, how are we handling this? It probably, let me look at this. I'm thinking what's going to happen. Oh, you got to be careful with this one, because if you use your formula, sorry, I'm having a math moment, you're going to get h over h is 8. Well, that would work. That actually makes sense. The formula does work. So what I'm going to do, and I'll show you why this is true. 32 All right, so we're actually out of time though. So the point is going to be this. I'll wrap this up. The point is this. D of t, which is distance, is 16t squared. And this is the distance measured in feet. The velocity, which was d prime, is 32t. And then the acceleration, which is actually d double prime, came out to just 32. And if you've ever had physics, or if you take physics, the acceleration of gravity in feet is 32 feet per second squared. Now, if it's in meters, it's 9.8 meters per second squared. So using the higher order of derivatives, we have this equation of ours, kind of the favorite, that tells us how far the pin falls when I release it. Well, the first derivative gives us the speed at that same time. And the second derivative tells us that it's always falling at 32 feet per second. The acceleration is the same. Now, indulge me just for maybe 3 minutes, and then that's it. We're done for today. I do want to show that the derivative of x is equal to 1. So we're going to take the limit as h goes to 0, and x plus h minus x over h. So this becomes the limit as h goes to 0. These will cancel. We get h over h. And it looks like we're headed for 0 divided by 0. But we want to remember that h isn't 0. It's almost 0. So that means we can do the cancellation first. And then this is just equal to 1. So the derivative of a variable by itself without any exponent, that's just going to be equal to 1. And so you could call this property number 8. All right. So that's it for today. I know there's kind of a lot there, and I know with that, like the continuity and everything. What I might do, well, I would recommend it. Well, I can recommend looking at the proofs. I could probably do some videos on those proofs. At least the continuity one, that was kind of interesting. But I just wanted to get through these 2 sections today. I'm going to post a review, and then I'll get those solutions for the pretest out as soon as possible. Other than that, thank you for staying later. Have a wonderful afternoon.